Alright, so today we'll be talking about simplifying complex numbers. Okay, we got to start talking about what the actual stuff is. Okay, so rectangular form of a complex number, and you'll understand why I'm saying rectangular because in a little bit we'll learn about the polar form of a complex number. Here it is. It's a real number. It's the real part right here, which is usually denoted by A, and the imaginary part, which is right here, which is B. Okay, so it's usually in the form of A plus BI. Okay, so in this case, A would equal 2 and B would equal -7. Okay, alright, so that one's pretty simple. Alright, now if B is not equal to 0, which this one is, okay, this would be called an imaginary number. So an imaginary number is 2 minus 7i. Okay. Alright, and that's a complex number being an imaginary number. Now if B is equal to 0, that means that all we would be left with is A, and so that would be a real number, and that would kind of just rule out everything. Okay. Now if A is equal to 0 and B is not equal to 0, so like something like this, 2i, this is a pure imaginary number. Okay. Right, and obviously this one right here, this would be 5. This is a pure real number. Okay, now we're going to learn some cool tricks with this. Real fast, you need to remember some tricks from your old school math days. But basically, you need to remember your rules. I is equal to the square root of -1, which is just I. Okay, so that's pretty simple. Now I squared is going to be equal to those two minus each other, so that's going to be -1. Okay, I cubed is going to be equal to -I, and I to the 4th is actually going to be equal to 1. Okay, and the cool thing is that we all know this is actually cyclical. It's going to start again up here. I to the 5th is going to be I to the 6th is going to be -1, I to the 7th is going to be I, and I to the 8th is going to be 1, and then it starts again, and it just continues to go around in its pattern. And that actually brings up the idea of something called iteration. Okay, now iteration is if we take the number from before and plug it into the answer after. It's going to be really interesting. So let's look at an iteration problem before we really start looking at all of this stuff. Okay, so just to figure out finalize our definitions, complex number is a number with a real part and an imaginary part. Okay, but first let's look at an iteration. All right, now before we start on iteration, we do need to talk about multiplication. So if we had 2 minus 5i times 3 plus 2i. Okay, something like this. So we would do our normal FOIL, or whatever method you want. So that first one would be 6, and then plus 4i minus 15i minus 10i squared. Okay, now everything's pretty normal here, except now we have an I squared. But if you remember, I squared turns into -1, and most math students make mistakes because they forget that fact. So this is 6 plus, well, this is actually 6 minus 11i. Okay, and then that's going to turn into a -1 right here. So this is going to turn into a -1, and -1 times -10 is +10. Okay. And so then we add those two together, and we should have 16 minus 11i. Okay, and voila, we actually have our problem all set up. Okay, all right, so when we get down to here, so if f of z is equal to 0.5 plus 0.5i times z, find the first 3 iterates for the value of 2 plus I. So for this is actually the initial value, for the initial of 2 plus I. Okay? Alright, so what we're going to do is we're going to literally just plug in 2 plus I. So this is going to be f of 2 plus I is equal to 0.5 plus 0.5 I, and then we're going to times that by 2 plus I. And if you notice, that set us up, this problem set us up for it. Okay, so what we're going to get is 1 plus 0.5, let's go 0.5 I plus 1 I minus 0.5. Now some of you guys are probably going, wait, where did that minus come from? Well, when I multiply these two, I'm going to get 0.5 I squared, but that's going to become 0.5 times -1, which is just going to become this. Okay, so what I get is this is my final answer. So I should get 0.5 plus 1.5 I. Okay, now that I got that answer, what I'm going to plug in for the next problem is I'm going to plug in this. So I'm going to literally the next iterate. So this is iterate number 2. I'm going to be plugging in 0.5 plus 1.5 I. Okay, and that is going to be 0.5 plus 0.5 I times 0.5 plus 1.5 I. Okay, and we do our FOIL, and so this is going to be 0.25 plus 0.75 I, okay, plus 0.25 I minus 0.75. Okay, and once again I'm using the I squared here to actually get that, and so when I write this out I should get negative 0.5 plus I. Okay, and now for the next one, for the third iterate, I'm going to plug in that. So what I'm doing is I'm literally plugging it into the next one. Okay, and so I should get f of negative 0.5, and guess what, this process never stops. This process will always be here. So it's actually kind of cool, but also at the same time kind of repetitive. Okay, where this is actually used in fractals, like the Mandelbrot set and everything, it's using an iterate with, especially with complex and polar complex numbers. Okay, and let's just finish this bad boy off. Okay, so 0.5, so that should be negative 0.25 plus 0.5 I minus 0.25 I, and that should become negative 0.5 I, or no, just negative 0.5 is what that one's going to become. And so now what we get is negative, let me see, negative 0.75. Okay, so as you can see, the real part is decreasing, not as much each time, but it is decreasing nonetheless. And then the imaginary part is also decreasing as well, but once again, not as. Okay, we had some technical difficulties, so I'll just write it out again. So this should become negative 0.75 and then this should become 0.25 I. Okay, and then if I wanted to find and continue my iterations, I would either tell a computer to do it, or I could do it on my own. I could just continue. So this would be the input for the next iteration that I'm going to work on. Okay, now what we're going to do is talk about complex conjugates, and then we'll be done for working with simplifying complex numbers. Okay, so on this one, I'm going to simplify it by rationalizing the denominator. So I'm going to be timesing by a fraction that is going to be equivalent to 1. Alright, now I'm going to use the complex conjugate. So if you guys remember from your rationalizing denominators with radicals, we're going to do the same thing, except instead with complex numbers. Okay, so I'm going to multiply top and bottom by the conjugate of the bottom, which is 7 plus 2i. Okay, all right. Now what does that get me up top? So that I'm going to have to FOIL out. Well, actually, I'll just work with the bottom first because that's just the easiest. When in doubt, go with the bottom first. Now this one is going to be, if you notice it, this is a difference of perfect squares, so it should be 49 minus 4i squared, and we'll come back to that. Well, we'll just finish it off. This should actually turn into 49 plus 4. Okay, because I squared becomes -1, and -1 times -4 is that. So this should all turn into a really nice number, which is just going to be 53. Okay, now up top I'm going to distribute, so that should be 14 plus 4i plus 10i minus 10. There we go. And the minus 10 comes about because 5i times 2i becomes 10i squared, which just becomes -10. Okay, so this top part is just going to simplify to 4 plus 14i. And voila, I have simplified the bottom of this actual expression. So if we get rid of this part right there, and let's move this over a little bit, we can actually shorten up that fraction, okay? Alright, and if you do everything properly, the bottom should just be one number that is real and should not be imaginary. That's it for simplifying complex numbers. Make sure you take time with your iterates, and have a great day. Bye.